Hello everyone, welcome to the channel. So in this video, I'm gonna show you the crop type detection using Sentinel-1 SAR Imagery in Google Earth Engine. So now let's get started. So let me explain about the Sentinel-1 SAR Imagery. So this is Sentinel-1 SAR GRD C-band synthetic aperture radar ground range detected log scaling. So the dataset availability is from 2014 to 2024. The dataset provider is European Union ESA Copernicus. And this is the code you can able to access this particular dataset, that is Sentinel-1 SAR Imagery. And these are the following bands that is available in this dataset here. So HH, which represents a single copolarization, horizontal transmit and horizontal receive, which is of 10 meter resolution. And HV is dual band cross polarization, and VV is single copolarization of vertical transmit and vertical receive, and VH is of dual band cross polarization, vertical transmit and horizontal receive, and all these bands are for 10 meter resolution. And last we have this band called angle, which has a resolution of around 20,000. So it is approximate incident angle from ellipsoid, so this particular angle. So now let us view the description of this dataset here. So the Sentinel-1 mission provides data from dual polarization C-band synthetic aperture radar instrument at 5.4 GHz. This collection includes S1 ground range detected scene processed using Sentinel-1 toolbox to generate a calibrated and ortho-corrected product, and collection is updated daily, and new assets are ingested within 2 days after they become available. So let me explain about this dataset here in detail. So Sentinel-1 SAR GRD is a dataset provided by Sentinel-1 mission, the part of the European Union Copernicus program. The Sentinel-1 consists of a constellation of 2 satellites, and Sentinel-1A and Sentinel-1B, which carries a C-band synthetic aperture radar instrument. These satellites are designed to provide a high resolution in all weather, day and night radar imaging for a whole range of applications, including environmental monitorings. So in the SAR imagery, we have C-band radar. Sentinel-1 uses C-band radar, which operates at the wavelength of about 5.6 centimeter, and the frequency is around 5.4 gigahertz. This wavelength is effective for detecting surface features and changes, especially in agricultural fields and urban areas, forest and water bodies. And next is a synthetic aperture radar. So the SAR technology allows the satellite to generate a high resolution image by combining multiple radar signals over the time period as it moves over the Earth's surface. This is essential for achieving the fine spatial resolution even when imaging is on large areas. So now let me get back to Earth Engine. So to perform the crop type detection using Sentinel-1 SAR Imagery in Google Earth Engine, first we have to define our region of interest. So for that, we define this variable called region coordinates equals to, we have mentioned the latitude and longitude of the study area here. You can able to visualize. Let me navigate the layer section. I'm going to turn this off. So to create a study area of your choice, just navigate this option here. Use this draw a rectangle, and just draw this rectangle over the study area of your choice here. So once you did, we have this this section here, the import one entry, and in that we have this variable called geometry, and you can able to see this option called show generated codes. I'm gonna click this. So here you can able to see the latitude and longitude of this particular study area. Just copy this, and you can just copy this and paste it here in this section here in the variable region coordinates. You can just paste it here. So once you paste it here, this study area will be created. So next we're going to create a polygon geometry using this defined coordinates, that is of latitude and longitudes here. So for that we define this variable called region geometry equals to geometry.polygon. So the region coordinates refers to this particular variable containing the latitude and longitude of the study area. And next, to add this layer, we define map.add layer, mentioning the region geometry with the default visualization parameter, and output the layer name as study area. And now to center this particular layer, we define map.center object region geometry with a specific zoom level of your choice here. So before performing our crop type detection, first we have to define our start year and end year. So to define the time period for our analysis, So first we define this variable called start year equals to, so we have mentioned the specific start year, that is 2020. So this particular dataset availability is from around 2014 to 2024. So you can select your year of your choice here from 2014 to 2024, and I'm gonna select for my end year, that is 2021. So the analysis will be performed from 2020 to 2021. So next we have to load our Sentinel-1 SAR image into Google Earth Engine. So for that we define this variable called Sentinel collection equals to image collection Copernicus S1 GRD. So this specific code will insert our Sentinel-1 SAR imagery into Google Earth Engine. So next we're gonna filter with specific date. So we have already mentioned the start year and end year here. So we're gonna filter with a specific year. So for that we define dot filter date, start year and end year. So the start year we have mentioned as 2020 and the end year is mentioned as 2021. So next we're gonna filter with a specific study area. So we have created a new study area here. You can able to visualize, and to filter with based on that study area, we define this dot filter bounds region geometry refers to a study area. So based on our study area to filter, we define dot filter bound region geometry. So filter by the our geographical region. And next is we're gonna filter with the. So the another property that it is essential to filter in the Sentinel-1 SAR imagery, it is the transmitter receiver polarization. So to filter with the specific transmitter receiver polarization, we define dot filter dot list contains the transmittance receiver polarization VV. So we have filtered by VV polarization. So let me explain about the types of polarization in details. So dual polarization Sentinel-1 GRD data typically includes two polarization mode, that is VV vertical transmit and vertical receive, and VH vertical transmit and horizontal receive. These polarization provides a different perspective on the surface scattering properties, which are useful for distinguishing between the different types of land covers. So let me explain about the VV polarization, that is vertical. In VV polarization, the radar transmits the vertically polarized waves and the receiver also detects the vertically polarized components of the backscattered waves. This means both transmitted and received signals are vertically polarized. And in case of VH polarization, it is vertical horizontal polarization. So in VH polarization, the radar transmits vertically polarized waves and receives the horizontally polarized components of the backscattered waves. This cross polarization mode detects the part of the signal that changes the orientation upon the interaction with the target. So the reason we are selecting the VV polarization, in images, area with a high VV backscattered appears brighter, indicating the surface that are rough or have a lot of vertical feature structures. Conversely, the low VV backscattered appears darker, typically indicating the smooth surfaces or the open water. So in case you are choosing VH band, so the VH band is useful in case of high VH backscattered typically indicates the areas with a significant vegetation or a complex surface features that causes a multiple scattering and depolarization. So the low VH backscattered suggests a complex surfaces with a less depolarization, such as the bare soil or spare vegetation. So let me get back to Earth Engine here. So the next important property to filter in the Sentinel SAR imagery, it is the instrument mode. So for example, we're going to filter with a specific instrument mode called IW, that is interferometric wide swath mode. We're going to select the specific that is interferometric wide swath mode. So to do that, we define dot filter dot equal instrument mode IW, referring to this interferometric wide swath mode. So let me explain about this thing here. So the spatial and temporal resolution. Spatial resolution, the resolution of Sentinel-1 GRD data varies, but it generally ranges from 10 meters, that is 10 to 20 meters, depending on the acquisition mode. For example, interferometric width swath and trip map, extra wide swath. So now let me explain about the interferometric wide swath. So the interferometric wide swath mode is one of the primary operational mode of Sentinel-1 synthetic aperture radar, which is used to measure a wide range of Earth observation applications. This mode is specifically designed to capture the high-resolution imagery over the wide area, making it suitable for applications such as land monitoring, oceanography, and disaster response. So the polarization about this IW mode can capture the data in both single polarization and VV, and dual polarization, that is VV plus VH or HH plus HV. The dual polarization capability enhances the ability to differentiate between the different types of land covers in surface conditions. The common use of this VV and VH polarization in IW mode allows for more comprehensive analysis of the surface feature, as it can capture both the vertical and vertical horizontal scattering information. So as the name suggests here, the IW mode is optimized for interferometric applications in SAR. It enables the generation of an interferograms which used to measure the surface deformations, topography changes, and land subsidence with high precision. Back to Earth Engine here. So in that we're gonna select the specific band called VV band. So for that we defined dot select VV band. So that is VV. So VV here refers to this particular band here, that is VV, single co-polarization, vertical transmit and vertical receive. So now to visualize the details of this specific image, we defined as a print Sentinel collection referring to this particular variable here. So we're gonna run this, and we're gonna click this option called run here. So here you can able to visualize in the console section, we have the image collection Copernicus S1 GRD, and we're gonna select the features, and I'm gonna select one of the image here, and in that properties, so we have variety of metadata that is available in this image here. So for example, the instrument mode, it is IW, the instrument swath is IW, and the orbital property pass is descending. So here you can able to observe here the orbital property pass is descending. So in this image it is mentioned as descending. Let me check in other images here. In the property sections here, we're going to check the orbital property pass. So it is also descending. So let me explain about this terminology in the metadata, that is orbital pass property about the descending and ascending. So let me explain about it. So the orbital properties of Sentinel-1 SAR Imagery, ascending and descending passes. So the Sentinel-1 is a constellation of synthetic aperture radar satellite operated by the European Space Agency. So it consists of two satellites, Sentinel-1A and 1B, that provides a coverage of entire planet with a high temporal resolution. So these satellites operate in both ascending and descending orbital paths, allowing for more comprehensive monitoring of the Earth's surface. Understanding these passes is essential for interpreting the SAR imagery accurately. So let me explain about the ascending pass here. So the ascending pass occurs when the satellite moves from south to north, passing over the Earth's surface. This generally means that the satellite is moving from the lower latitude to higher latitude, typically during the local night or the early morning hours. So the orbital path, during an ascending path, the satellite's orbit takes it from a southern hemisphere to the northern hemisphere. The ground track of the satellite moves from west to east due to the rotation of Earth. Next is a descending path. A descending path occurs when the satellite moves from north to south, generally passes over the Earth's surface during the local daytime or the afternoon. In this path, the satellite travels from a higher latitude to lower latitude. The orbital path, during the descending path, the satellite orbit moves from the northern hemisphere to the southern hemisphere. The satellite travels westward in its orbit while the Earth rotates in eastwards beneath it. So this is about the ascending and descending paths in the Sentinel SAR imagery. So let me get back to Earth Engine. So in the next step, we're going to separate the images into ascending and descending orbit paths. So you can able to see from this image here, so we have around 241 images for the specific study area. So in that, each image has ascending and the descending orbit paths. So in order to separate them, so we're going to define this, we're going to separate the images into ascending and descending orbit paths. So now to separate the images into ascending and descending orbit paths, so we define this variable called ascending path equals to Sentinel-1 collection. We're gonna filter dot filter doubly dot filter dot equals orbital property pass referring to the metadata equals to ascending. So we are still filtering based on the ascending orbit. So now to visualize the details of the image, that is for ascending images, I'm gonna mention as print, and I'm gonna mention the variable here, the ascending pass. I'm gonna paste it here. So once you did that, we're gonna run this code here. I'm gonna click run, and we're gonna visualize how many of these images are of ascending image in this particular study area. So here, so there is total of around 119 elements which are of ascending image. I'm gonna click this arrow in the console section here. We can able to visualize here the features. I'm gonna click one of the image here in the properties and navigate to the orbital property pass. So this is the ascending image. So you can able to see from this image the orbital property pass is of ascending. So similarly, there is around 119 images that are of ascending image, and similarly to check for the descending, we're gonna define this variable called descending pass equals to Sentinel-1 collection dot filter doubly dot filter dot equal orbital property pass descending. So now to view the details of this image, that is number of images that is of descending image, we're going to mention as print, and we're going to mention the variable here, that is descending pass. I'm going to copy this and I'm going to paste it here, and again I'm going to run this code here. So now when this image, let's visualize the number of image. So there is around 122 elements, that is images, that is descending. You're going to click the features here, and I'm going to select one of the images here, the properties. So you're going to visualize here the orbital property pass, that is, this is of a descending type image. You can able to see from the metadata of this particular descending pass, you can able to see that. So there is around, you can able to see from here, the descending is around, so it is around 122 images, and the ascending image is around 119 images. So basically I could like to prefer saying that both ascending and descending orbit pass images are both are good. So if you are using both this ascending and descending image together, it is good, and it increases the accuracy of and the reliability of your result. For example, let me explain it once more again here. So ascending pass. So this occurs when the satellite moves from south to north. During this pass, the satellite captures an image while it is ascending from a lower to a higher latitude. The local solar time for ascending passes typically falls in late afternoon or evening. So the descending pass, this occurs when the satellite moves from north to south. During this pass, the satellite captures an images while the descending from the higher to a lower latitude. So local solar time for descending passes typically falls in early morning. So if you're getting confused to use which one of the which one of the orbiting paths should be used, so I prefer using both of them. For example, the choice between ascending and descending paths largely describes on the specific applications and requirement of the study. For example, monitoring using both ascending and descending paths is generally better. This approach provides a more frequent and update and more complete view of the study area, helping to capture the changes that occurs at different times of the day and from the different viewing angles. And for specific time of the day study, if your study focuses on the phenomena that are time sensitive or have a daily cycles, for example, urban heat islands, daily water use, so the choice of the path should align with the time of the events, should align with the timing of the event. And for interferometry, using both passes is advantageous as it provides a different viewing geometries and improving the accuracy of the displacement measurement and help to resolve the ambiguities. So now let me get back to the Earth engine. So and also in the console section, you can able to view that first is of it is our ascending. It is total images around for 119 images, and for descending is around 122 images for the study area. So number of images is almost kind of same for this particular study area. So next we're gonna calculate the monthly average of the ascending and descending image. So in this step we're gonna convert the weekly average image to a monthly average for both ascending and descending images. So now to calculate the monthly average of both ascending and descending images, we define this variable called monthly SAR equals to image collection list sequence, referring to the months here. So 1 to 12, referring to the number of months in a year, and map function. So we define map function months here. So we are starting from the first month to the last month. So then I will do some sort of processing based on the number of months I have in the each input of in the function is considered. So it is considered as a month here, and so next we're going to make two different variables, that is ascending monthly and descending monthly. So for both ascending images and descending image, so first for ascending image we define this variable called variable ascending monthly equals to ascending pass dot filter dot calendar range. And the calendar range is one of the most popular function in the Earth Engine. So here we have specified the start month to be a month and the end month to be month and output as a month. And this particular which refers the field here, so field we are referring is the month here to get in the monthly format. So for the each month to get a mean monthly image, so we define dot mean function and dot rename as ascending. And similarly, we're going to define this variable as a descending monthly for the descending image here. So equals to descending pass, referring to this descending images here. You can able to see this variable, and in that we're going to dot filter Earth Engine dot filter dot calendar range, and start month we defined as month and the end month as a month, and the field we are referring is a month. So now to get a mean image out of this descending images, for monthly mean images, we define dot mean function and dot rename descending. So next, now we want to have a new system time start explaining the date of creation or the date of acquisition for the new images. So now to do that, we're going to define a variable called date equals to dot earthengine dot date dot from YMD, that is year, month and day. So starting with the year, we defined as 2020. So here the 2020 which refers to the time start, that is 2020. So the next will be updated based on the input months here. So we're going to leave it as a default here as a month. And the next is the day here. So the day 1. So we're going to specify as the day 1 here. So last we're going to return the ascending monthly images. And we're going to add our we're going to add descending monthly using this add bands here. So the add band function that allows you to make a stack layer from both the ascending images and also from the descending images for each date for each month. So now the new stack layer needs a new property or the metadata file. So dot set function here that allows you to make a new properties. So for that we define dot set system time start comma dot date millisecond function here, so to convert to a millisecond format. So we are using this millisecond function because the Earth Engine utilizes this particular millisecond format for temporal analysis. So that's why we are using this millisecond function here. So now we're going to set a new property here. So for that we have used this dot set function here. So we are creating a new system property, that is system index, and we're going to mention as a date dot format as a string format. So to be mentioned is as a string format. So we have used this to show that in the yearly and month format. I've done it to have used this y here dot m. So now to visualize the details of this image here, so let me show you that here. So I'm going to enter as print and I'm going to mention the variable here, that is our monthly SAR. I'm going to copy this and paste it here, and I'm going to run this code. I'm going to click this option called run and click run. So now we're going to visualize the details of this particular monthly average ascending and descending, And also we set the system time start and system index here. We're going to check this out. So navigate to the console section here. I'm going to click this arrow, and here you can able to see we have 12 elements. These are the different images here. I'm going to click one of this image. So in the bands we have both ascending and descending in double format, double data type, and projection coordinate reference system. And in the properties we have created new system index and systems time start. So the system index here refers to the year and monthly format. You can able to see from this the code here. And similarly, and in the system time start, so we have mentioned as in millisecond format. So to view it in temporal analysis, so we have mentioned as a date dot millisecond. So you can able to see in this in the millisecond here. So this is June 2020, and this one here refers to, you can able to see here. So you can click this properties. So it is January 2020. So now we have managed to calculate our monthly average ascending and descending images here. So I can able to see that. So now next we're gonna apply the speckle filtering to reduce the noise in the SAR image. So for that we define this variable called speckle filtered equals to monthly SAR. So we are referring to this particular variable here, the monthly average ascending and descending images here. So we are referring that, and dot map function, so referring to the image here, and we're gonna return image dot. We are using this particular focal mean function. So this particular focal function is a method that applies a focal operation, which means it computes a mean value of pixel within the specified neighborhood around each pixel. So the 30 is the radius of the neighborhood specified in meters, and the filter will take a mean of all pixels within 30-meter radius around each target pixels. And the square here, which specifies the shape of the neighborhood as a square, and the meters specifies the unit of the radius, ensuring that the 30 refers to the meters, not the pixels. And next we're gonna copy this property. So we have defined dot copy properties image comma image dot property names. So after applying, we have applied the speckle filter, and this part here ensures that the metadata properties of the original image is retained in the filtered image, and the copy property function copies the specified properties from the source image to the output image. And the image dot property names here, which refers to the retrieves the list of all property names from the source image. This includes some metadata such as image acquisition date or the orbit number. So now to add this layer, to add the ascending and descending SAR layer to the map based to be clipped based on our study area, we define map.addLayer. So now to add this layer, we define map.addLayer speckle filter dot select. So we are referring to this particular variable here after applying the speckle filtering to reduce the noise. So we are referring to that, and speckle filter dot select ascending. So we are referring to ascending images here, and to view this image as a stack layer, to view all the images as a monthly images. To do that, we define dot to band function and dot clip based on our study area with the default visualization parameter, and output the layer name as an ascending SAR. And next, similarly, to add the descending image here, we define map.addLayer speckle filtered dot select descending. So we are referring to the descending images here. Dot two bands to stack the layers as a monthly images. To view that in monthly images as a stack format, we define dot two bands function here, and dot clip based on our study area with the default visualization parameter, and output the layer name as descending SAR. So now we're gonna visualize it. We're gonna click this option called run here, and we're gonna visualize the result. So now let me reduce this and navigate to the layer section. So we have this layer called ascending SAR. I'm gonna click this, and let me turn this study area off here. I'm gonna turn this off, and you can able to visualize this image here. So now we're gonna click this option here. We're gonna click this option. So now we have ascending SAR visualization parameter here, So now to make it as a multi-temporal image, so here you can able to see we have three bands here referring to RGB that is refers to red, green and blue. And here in this band you can able to observe the ascending image for the month of January, which is represented as 2020-01, and for February it is represented as 02. So now we're gonna select this particular month here. I'm gonna select June here, and here I'm gonna select April. So I'm gonna select this one here, and for this particular band I'm gonna select as February. And in the to adjust the contrast of this image, we're gonna navigate to the custom section here, and in that we're gonna click this option called stretch 90%. And once it's applied here, so you can see the range here, and I'm gonna click apply. So now we're gonna visualize the result here. So I'm gonna zoom to this part of the study area here. So you can able to visualize the different colors here. Let me turn to a satellite image here, and I'm gonna make it down and turn this off. You can able to see this agricultural area in this image in the base map. So this is a SAR image. So basically this is the multi-temporal combination of SAR imagery. So for example, in this video you can able to see that each color of this set of crops here are shown in the different colors. So the each of these colors represents the different crop type in the study area. You can observe a variety of crop colors here. You can able to see that, and I can also adjust this contrast color. So I can adjust the contrast to 2 sigma, and I'm gonna apply this here. So now the color is much visible compared to the earlier one here. So you can able to see that. Gonna minimize it, zoom it out, yes. So gonna view it in the toggle in full view here. So now you can able to see this image clearly. So in this SAR image you can observe a variety of terrain features here. So we're gonna specifically focus on this crop type here. So you can able to see the similar color which shows us a similar crop type, and you can able to see here the green portion here which represents a similar crop type, and this set of colors here you can able to see here. I'm gonna turn this off. You can view in the satellite mode here. So similar color which represents a similar crop type, and you can able to see a variety of different colors here which indicating the different crop type that is available in this region. So similarly, now we have visualized our descending star here, that is our ascending star. So now let us visualize the descending SAR image. I'm gonna click this. So now we can able to visualize the descending SAR image. I'm gonna click this option here. Let me minimize this, and now you can able to visualize the descending SAR image. And I will close this, navigate to the layer. I'm going to click this option, and similar to that, so we're going to select this particular month here. So I'm going to select July and June, and I will select April, and here I'm going to select February. And the contrast, you can adjust the different contrast level. So I'm going to mark it as sigma 2, and I'm gonna apply it. So you can able to see the value here. I'm gonna apply. So now here you can able to visualize it. So now here you can able to visualize the image, that is descending SAR image here. I'm gonna click the toggle full view mode here. So here this is the descending SAR image, and I'm gonna turn on the ascending too. I'm gonna visualize the difference here. So you can able to see the changes here. So descending SAR versus ascending SAR image. This is ascending SAR image, and this is the descending SAR image. So now for the interpretation of this SAR image here. So using SAR data for the crop type detection, the seasonal variation. So the different crops have a distinct growing seasons and the canopy structures. By observing the changes in the backscattered over time, one can identify the growth cycle and the crop maturity stage. the structure and moisture content. The crops such as rice, wheat, and maize have a different canopy structures and moisture content, affecting how they scatter the SAR signals. For example, the rice field during the flooding stage will have a different backscattered signatures compared to the dry wheat seed. So now let me get back to the Earth engine here. So you can able to see the difference versus the ascending versus descending image here. So this is ascending SAR image, and this is the ascending SAR image, and this is the descending SAR image. So let me toggle this. So I'm gonna close this, and I'm gonna bring this down here. So next to define a point for the time series analysis. So we're gonna define a point here. So for example, I'm gonna navigate this point here. I'm gonna click this, and I'm gonna add a marker the point here. So now in the top you can visualize this particular entry here. So I'm gonna click this variable define the point data. I'm gonna click this one here. So you can able to see the latitude and longitude of this point data here. So this is the type point. So this is the point data, latitude and longitude. I'm gonna copy this, and I'm gonna paste it here in this section here. So I'm gonna paste it here in the time series point. So I'm gonna paste the latitude and longitude here. So once you paste it, we can perform our time series analysis. Let me turn this off. So to generate and print a time series chart for the SAR backscattered value at the specified point here, we define print ui.chart.image.series speckle filtered time series point AA.reducer.first function. So we're going to create a time series chart here. So the speckle filter refers to our noise removed of Sentinel-1 image, and the time series point refers to the point data that we created to perform a time series analysis. And the reduce region, AA.earthengine.reduce.first function here. And next we set up a spatial resolution to be around 10 meters. So the SAR image has a spatial resolution of around 10 meters, and the system start time referring to our start time of this image. So we have previously mentioned as 2020. So the system start time refers to 2020 here. And in that we're gonna set options. So we're gonna specify the title to be SAR backscattered time series, and the v-axis we mentioned as the title as backscattered in so the dB refers to so the dB here refers to the decibels, the unit, and the h-axis represents the title as the date, and line width is around 1, and the point size given to be around 4. So now to run this code, we're gonna click this option called run here. So I already run this code here. Let us check out the graph is given here. So now in the time series chart in the console section, you can able to see the variation in the ascending and descending here. So in this axis, is the backscattered in decibels, and this axis represents the date, and the title is the SAR backscattered time series. So the blue indicates the ascending, and the red indicates the descending. So you can able to see that variation in the ascending and descending section here. You can able to see that. So basically this ascending and descending is taken from for the same study region. So you can have already shown you that example here. So there is a slight variation in the graph you can able to see here. So there is a slight variation in the graph for ascending and descending, is because this occurs that satellite moves from in case of ascending, the satellite moves from south to north, and in the case of descending pass, the satellite moves from north to south. So because of this angle of view, which causes the different backscattered values as we see in this graph mentioned given here. So let me click this option here. You can able to view the graph more clearly. So you can able to see the backscattered values has a slight variation for this both ascending and descending. So you can able to see that. So that's why I'm suggesting that you use both these images as a separated variable. Also using this both the combination of this image will increase the accuracy of your analysis, because the ascending is kind of moving from south to north, and the descending is moving from north to south, which results in slight variation in our backscattered values here. So you can able to see that here. So it is kind of similar, but has a slight variation in these values here. And also the time series plot starting from January 2020 to December 2020 here. So you can able to see in this period of month from starting from January to till April, the backscattered value is kind of low here, and after that, after from April onwards, the vegetation, the backscattered values begins to be higher, having higher reflectance compared to between this starting from November to April has a lower value, which indicates so in this particular months has a lower vegetation compared to the set of months here from April onwards to till November. It has a good vegetation comparably. Then the June to September it has a good vegetation, has a good backscattered values. Compared in this month has a lower backscattered values. So when here you can able to see in the descending image here. So this particular month has a higher values. So starting from especially in July and August has a higher backscattered value. So let me navigate to the Earth Engine section. So in the image here, so I'm gonna turn on the descending, and in that I'm gonna select this particular timeline. So we have seen in the graph earlier. So I'm gonna select the first band as August. I'm gonna select August and July and this June, and I'm gonna select this per set of timeline here. Custom I'm gonna select to be 2 sigma, and I'm gonna apply this. So now let us visualize this result here. So only in this specific months here has a higher backscattered value for this specific region we this mentioned here. So you can able to see the point data here. Gonna turn this off. And similarly for this particular, we're gonna check for the ascending. So in the ascending, the highest level of backscattered value were observed in this set of months here, starting from April to till November. So I'm gonna select in August, July and May. So let us visualize the result, and we're gonna turn this off and we're gonna turn this on and click this value. So we're gonna select as an August here, and here I'm gonna select June, and I'm gonna select this part, and I'm gonna select May, and select the contrast here. I'm gonna select this particular contrast to sigma, and I'm gonna click apply. So now let us visualize the result. So you can able to see from this image here. So you can able to see the different crop types and different colors. This portion has the different colors indicating different crop types that is available in this study area here. You can see a variety of different colors indicating a different crop types. So I'm gonna close this. Let me zoom out. So now we have visualized our ascending image here. So next to export this image into to Google Drive. So let me show you that here. So now to export this SAR image, sending SAR image to your Google Drive. So I have defined export.image.to-drive, image speckle filter.select ascending dot two bands dot clip region region geometry referring to our region of interest. And similarly, we have a description. We have given as SAR ascending, and the spatial resolution we are giving given as to be around 30 meters. And the region is our study region, that is region geometry refers to our region of interest with the max pixel values, and the coordinate reference system. And the folders we have defined crop type analysis ascending. And similarly, to export the descending SAR image to your Google Drive, I have defined as the export.image.to-drive, image speckle filter.select descending two bands dot clip referring to our region of interest, that is study area. And description SAR descending, spatial resolution, and the region is our region geometry referring to our study area, the max pixel value, and last the coordinate reference system. And similarly the folder crop type analysis descending. So now to export this to a Google Drive, click this option called run and run. So now in the task section, click this option called task, and there is a task called an unsubmitted task, SAR ascending and SAR descending. So now to export this image to your Google Drive, just click this option here. So we have new window saying initiate an image export. You can just export this, leave it as the default, the coordinate reference system. So scale, and we're gonna upload to our drive. So you can also select your cloud storage or e-asset section here. So to export this to a Google Drive, click this option called run. So now let us take a look at the applications of this particular studies, the other applications. So the application of the other applications for this data set. So agriculture, monitoring crop growth, assessing the soil moisture, and detecting the changes in land use. The ability to penetrate the cloud and operate at night makes the SAR invaluable for a consistent agricultural monitoring and flood mapping and disaster management. The Sentinel-1 all-weather capability allows it to effectively map the flood events, landslides, and other natural disaster, providing a critical data for emergency response. And the urban development, so monitoring the urban expansion, infrastructure development, land subsidence, which are the important for the urban planning and management. And forestry, assessing the forest biomass, detecting deforestation, and monitoring the forest health by analyzing the changes in the backscattered value over time. And last, the water resource. So mapping and monitoring the water bodies and detecting changes in wetland areas and assessing the extent of inundation during flood events. And the codes will be given in the description. So in this video I have shown you how to identify the crop type detection using Sentinel-1 SAR Imagery in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and like our channel. Thanks for watching.